All right, today we're going to talk about priority queues.
Yay.
You already talked about queues. So priority queue, as the name implies, means that when you add something to the queue, it's going to bump it up into the correct spot along the queue based on its priority.
Whoa.
Anyone
Crazy how that
confused about
works.
this?
Sure.
No, what are you confused about?
Nothing really.
Okay, good. Good.
I was looking at the slide so I could.
Now, we're going to discuss this in some detail, and then we're going to think about how it's implemented. And there's a real easy way to implement priority queues that we've already talked about, so start thinking about that. Because this lab can be really easy or really hard depending on which way you want to do it. Yes, Sydney?
Why are the second U and E silent in Q?
Because it's not, probably because it's not an English word.
Is it French?
If the spelling is messed up, the chances are high that yes.
Q.
No offense to the French, just from an English speaking standpoint, yeah, what are you doing?
I don't think anyone's French in the class.
Okay, I'm
Speak French.
technically Cajun, but whatever.
What's Cajun? Bonjour.
It's
Ooh.
the French people that went to Canada, came from Canada down to Louisiana.
So you're Canadian?
Actually,
sure.
that means he's technically French.
Alright, here.
Yes,
look it up.
technically.
Look it up.
Technically.
Okay, it does come from French, actually.
Well, yeah.
So you're
I learned about it in
Canadian?
French history.
Cajun, yes. My
Cajun?
grandfather was 100% Cajun,
Because it was.
officially.
I was going to say it was French. Officially?
And yet somehow you ended up in Texas.
It's right, Louisiana's right next to Texas.
All right.
Man, you're a northerner.
Woo!
Cool.
Hey, I'm a northerner and I knew that.
That's true.
Yeah, but you went to high school over in Columbia.
And Yankees.
Yeah,
All right.
but I knew it before that.
I've only been here for 1 year.
All right, so priority queue. So a stack is first and last out. A queue is first and first out. Everyone remember that?
Sure.
Yep.
So a priority queue is least first out. In other words, your priority is the lowest number.
So it
The
doesn't
smallest
matter where it
element is the first one. What's that?
So it doesn't matter where it is in the queue. It's
Queue.
first.
Well, no.
The smallest
The
item
order's
should
already
pop
there.
out first.
Yeah.
Right.
You have it ordered by the priority.
You're going to have it ordered by the priority, right?
So the lowest
Sorting.
priority is already going to be there, like
Sure.
at one of the ends.
Oh, this almost kind of reminds me of that lab from Java, where you have like the medium, low, and high priority.
Yeah.
Not
Yeah.
Did we ever
Yeah.
complete that?
I did, but
I
it
did.
didn't work properly.
It was
Wow.
annoying.
Like,
but-
it worked, but it was only like based off of 1, 2, and 3.
Anyways, you could also define the large. Well, that was
Oh, I
actually fun.
remember that one.
You could also define this largest first out if you want to, which is basically the same thing. You just reverse it, so no big
Yeah.
deal. So smallest is up to the programmer, meaning that if you were writing this in Java, you would implement comparator or comparable. But in C++, you just overload the less than operator.
Yes.
Overload.
Yay!
Mind that.
I hate overloading.
I agree. If
I
there's
just overloaded it for my extra credit for my scripting test.
if there are several smallest elements, the implementer must decide which to remove first, so it doesn't care which. All right, priority queue. Here's one possible abstract data type. So you create the priority queue, you can add something to it. Wow, these are Java slides. What's this doing here? Oh, well, I need to update these.
What's this doing?
You can add the element, you can remove the least, get the least, is it empty, and ask for its size. Okay, that's nice. And clear it. And Java added priority queue in Java 5, but we don't care about that.
We don't care about Java.
No, we don't. All right, so anyone confused about what the priority queue does?
So it handles the lowest priority first.
Right, if someone's added and they need to be bumped up in the queue, it pushes them forward, right? Do you think this is used a lot?
Yes.
Yeah.
No.
What? No? No? Yes? All right, why do you think it's not used a lot?
Well, how many times is it actually used? It's only used when it comes to elevating, say, people of priority. Like administrator, in that sense I can see it, but for the general consensus of creating general computer software, no.
Well, I mean, if you have someone in there and they have an immediate need, well, hospital sounds like it jumps to my mind. You're doing triage.
Yeah.
And it's like the highest priority first.
Right, yeah, if you need an automatic triage type system,
Like
that would
if-
jump in.
And if you came in with a broken tooth and then somebody's bleeding out, you take the person that's bleeding.
Right. You
Right.
take the one bleeding
Yeah, I
most
can see that.
buttons.
No, broken tooth is more important.
Okay.
I could just imagine
That's
all
why I
of the
waited
words
3
in
hours when I
French.
broke mine.
Wow. So, yeah, priority queues are actually used a lot. So we need to think of a data structure. All right, so in order to think of the data structure, we should first look at the usage patterns. So if we load the array in once, do 1,000 searches on it, we want to make searching fast. So we probably want to, huh?
How about a hash?
We want to hash. So you want to hash the priority queue? How would that work?
When in doubt, hash everything.
When in doubt, hash it out. You know, I did say that last time, but a hash table is going to be terrible for this one.
So you
Dude,
lied
every-
to us.
Yeah.
Every time.
So I don't know why you said that.
You
I
don't
said
have
that
to-
because
We're
most of
in
the
doubt
time,
now.
when you're coding, you just want to retrieve something very quickly, and that's why you use a hash table. But this time, we're going to do something a little different.
And now I'm in doubt.
Good.
And I
I'm
can't
glad.
hash it out.
I'm glad. If I've taught you anything with data structures, is always be skeptical.
I've already.
But I can't
doubted
hash it out
everything,
now.
So.
Good. All right. So we want to load in a huge array, maybe do some searches. We probably don't want to spend time sorting the array. We just want to put something in it real quick, because usually when you have this priority queue, you're adding and removing online, right? It's not like you have the whole data set and then you, yeah, online. You never heard that term?
No, I said on the line.
On the line? On the line?
Interview.
On the line.
Online.
Shia LaBeouf.
So we want something else. We don't want to have to sort it every time we add something, and that would be kind of terrible. So we really want to analyze add. Neither add nor remove is important. We need to look at timing for add plus remove. Is basically what this comes down to, because we're going to be adding or removing while the thing's being used. So we need to optimize those two operations. All right. So what's the first data structure you probably want to choose? Okay, an array. How?
Everything is arrays.
You could implement it as an unsorted array. Adding an element would take O of 1. Why? Why?
Because you just put it in the spot.
You just put it at the end.
O of 1 in the best case.
Yes.
Because sometimes you have to double the size.
Right. So if it's unsorted, it takes O of 1, we'll say on average, but removing takes O of n. Why?
Because you have to look for it.
You have to look through the entire array.
That's annoying.
That is annoying. Silly arrays.
Life is annoying.
Hence, adding and removing takes O of n, which is not good. This is inefficient. We could use a sorted array. All right. So adding would take O of n. Why is that?
You have to find where to put it.
Yeah, you got to find where to put it and then shift everything down. Huh.
Boo.
Boo. But removing would take O of 1. Why is that?
Because you know where it would.
Yeah, you know where it is.
Yeah.
All right. But adding or removing takes O of n. Well, that's a terrible solution. What's another solution? What's the next data structure we use?
Linked list.
All right, let's do a linked list.
Even though that's a horrible solution anyway.
Yeah, well, we got to go through all of them just to tell you. Adding an element would take O of 1. Why is that? If it's unsorted,
You just add it.
you just add it. All right, that's cool.
Search would be O of n, and I know this personally because you have to iterate through the whole linked list.
Sure. Well, hold on. Removing is taking O of n. Why is this?
Because you have to search through the
Yeah.
thing in order to get it.
So that's not good. How about a sorted array or a sorted linked list? Adding would be,
O of n.
oh man, this is doing terrible. Removing would be O of 1. All right.
Wait, why O of 1?
Well, if you sort it to where the last element is the one that needs to be removed, then you just push your back pointer back one. And if it's a doubly linked list, you just push it back by one.
Oh,
You're
right,
good.
right,
You're
right.
good to go. So yeah, that can still be O of 1. So as with arrays, adding or removing takes O of n. All right, so we're going to say a linked list and an array is a terrible solution for a priority queue.
Especially for the first project.
Yes, it is. What do you think we should try to use next?
Binary tree?
All right, let's try a binary tree. So binary tree. What would adding to a binary tree be like?
O of 1.
So a not balanced one would range from log of n to n. Why is this?
Because you have to find where the end of the branch is.
Yeah, but why could it range from log n to O of n if it's not balanced?
Because we go like 10 on one side.
Yeah, so the binary tree, if it's not balanced, could essentially turn into a linked list.
Oh,
Yes.
So that's inserting. How about deleting?
O of n.
Yeah, log of n to O of n, again, depending on where it is. So, all right, how about a balanced one? What would insertion be for a balanced one?
Log event.
Log in to all event.
If it's balanced, it should just be log. Insertion and removal could destroy the balance, so we need an algorithm to rebalance it. Good rebalancing ones take log of n. And hopefully if you've worked on your project by now, you'll have seen that this rebalancing algorithm is not fun. Yes?
Yeah, especially red black, but I'm not doing that.
Right. But
Did
are
anyone start their
complicated.
projects?
Huh?
Did anyone start the project I started one?
I hope you all have. All right, so we're going to say that a binary tree is not the best solution. What other data structure could it possibly be?
A heap.
A heap. Why would a heap be a good solution to this?
Only other data structure I can think of.
The only other data structure. So let's look at a heap implementation. So if we implement it as a heap, we define the heap property, and the heap property is going to be at least as large as its children. So, for example, your left, remember your left is not going to satisfy the heap property, so you'd have to switch the 3 and the 12, and now we have something that satisfies the heap property. Y'all remember heaps?
Yes.
Okay. What was nice about a heap?
It's all one.
Let's go with one. What was?
And what context?
Yeah, what?
Searching?
Searching is okay. Sure, getting the lowest element. Well, finding the lowest element's O1, but removing it is
All event.
not
Log
O1.
event.
Log event. Why is that?
Because you have to move stuff to where it was.
To move stuff to where it was. So what data structure did we use? Basic data structure did we use to implement a heap?
Array.
An array. There we go.
Away.
An array. So, for example, this heap could be represented by this array. Last index at 5. For those of you who need a quick refresher, 3's at the front, its children are 12 and 6. Now the 3's on the top, then goes 12 and 6. 12's children are 18, 14, hence afterwards they're 18, 14, and then 6 is 8, and we haven't gotten to the other one, so 8 and over.
Can there be a 17 and a 38 after?
17, so you could put a 17 right here. You put the 17 here, it would be at this one, and then you're asking for 38. Yeah, 38 would be in this spot and would be represented in this location over here.
Okay.
Okay? All right. What's nice about this is the left child of node I is always 2 times I plus 1. The right child is always 2 times I plus 2. That's nice. Unless your computation yields something larger in last index, in which case there is no value. Parent of node I is I minus 1 divided by 2, unless I is 0, because then you have
Null.
no parent. Okay, using a heap, just quick refresher, increase the last index, and then you add a node, and then you bubble it up, or percolating up, that was cool. Up the heap, and this requires log of n time. Why is that?
Because you have to go through half the array to put it up.
Yeah, well, you jump half the array each time while you're putting it up, essentially. So it's log of n because you're dividing by 2. Do y'all see that? Does anyone need me to draw that out? Okay. You do? All right, great.
Not quiet today.
All right, let me draw this on the board. People keeping track at home, I'm just taking this picture and putting it up on the board. It's quiet today. Yeah, why is it so quiet today? Oh wait, we already had our fun discussions this morning.
Yeah.
Yep, and a meeting.
They were depressed.
And you're depressed?
No, I'm just eating.
You're eating or cheating?
Eating.
I thought you said you had a meeting. Like, why would you have a meeting?
Any other ways we could figure out how to misinterpret what Sydney just said?
She's being mean.
I don't think she's being. Are you being mean?
No.
Am I mean?
No, I don't think she's mean.
Yes.
Wow.
Wow.
She's abusive.
Ooh.
I don't know.
I'm not abusive.
Wow,
Well, actually,
friends really are the
probably.
meanest.
She's a very abusive person.
She's a very abusive person.
Apparently.
All right, let me go back.
I mean, I don't see it.
All right. All right, so here's the heap up here, satisfying the heap property where everyone's parent. Let me rephrase that. For every node, its children are larger than it. And therefore, its children are always smaller than its parent. In other words, 3 is less than both 12 and 6. 12 is less than 18 and 14.
You mean the parents smaller than the children?
Yeah, we have small parents.
You said children are
Smaller than parent.
Yeah.
Now you're just confusing
Yeah.
everyone.
Well, right here, the parent is always less than the children.
Yeah,
And the
you
children
said
are
that, and then you
great.
said that the children are always smaller than the parent, and we're like,
Thanks for correcting me. The children are therefore larger than the parents, yes.
Basically, it's an unbalanced tree, so the children are going to be bigger than the parent.
This is a balanced tree. This is a balanced left justified
balanced.
tree.
Oh.
It's balanced because
Yeah, I see why.
every row is full except the last one. And it's left justified because on the last row that is not balanced, all the nodes are pushed to the left. So a heap is always balanced and left justified. Right?
Yeah. Whatever the
No
professor
love.
says.
Whatever the professor says. So the array implementation, or picture of this, you have a 3 up here, followed by a 12 and a 6, followed by an 18, 14, and 8.
yep.
18, 14, and 8. All right. Someone give me a number that's less than 3.
2. 2.5.
2.5.
Negative?
Yeah, it could be negative. Negative 2.5. Thank you so much. Whoa!
We're breaking all the rules.
All right. So when you add something, you put. What rule are we breaking?
I love how it took him a second.
This is so much better in Java.
All right. So the first thing is you insert it at the end of the array. That is O of 1, correct? Always. All right. We're good there. But it's not in the right location, so we need to percolate up or sift up. So what do we do first? We need to compare it with its parent.
It.
The child that we just added with the parent. And that's so it's negative 2.5 and 6. Is negative 2.5 less than 6? Yes. So we need to swap it. So we'll go and take this guy, and swap them. All right, and then we do it again. Negative 2.5, and the 3, negative 2.5 is less than it, so we need to swap them again. Okay, and we're done. Now the question is, how many times did we have to swap?
Twice.
3 times. We had to swap twice. Sure, whatever. The
A number.
But more specifically, how many? Can you tell me a relation to the number of levels in this tree to the maximum number of swaps? Is there a correlation to the number of levels in the tree?
Yeah.
Right. So you have to swap basically at most the number of levels, aka the height minus 1. Now, the reason I'm saying that is every time you increase the height, you double the size of the heap, right? And so every time you sift up, you're basically dividing it by 2 how many times? Because you didn't have, when you went from here to here, you didn't have to compare this end for it. You only had to compare this end, or this piece of it. So that was cutting off essentially half of the tree for you. And since you're cutting it off each time, it's log base 2 of n while you sift up. Is that clear?
Yeah.
Awesome. Is that better? Was that good?
Yes.
All right.
C.
Si, senor. All right. Okay, great. So you add an element and you bubble up. To remove an element, do you recall what you do there? Let's go and do the remove as well. So if we're going to remove, what do we remove in the heap? There's only one element we remove, and that's the top one, the parent.
Yes.
So we remove the parent, and then, what's that?
Everything else dies.
No.
If you take the roots off of a tree, the whole tree is going to die.
This is an inverted tree. Remember, the leaves are important, not the root.
Yeah, I guess.
And then what do we do after we remove the head guy, the headmaster?
Move the right side.
Not the 3. We remove
The lowest value.
the last. No, we remove the last value of the heap, the one at the end.
Oh yeah.
And
That's it.
why do we do that? Does anyone remember?
Well,
We do that because then that forces the heap to stay balanced and left justified. Because the whole point of the heap is to keep it balanced and left justified so you can keep it as an array implementation.
Right.
Right.
Sure.
But is this 6 in the right location?
Yeah.
Yeah. So we need to find which one to replace it with.
3.
3. Okay.
I don't know, I think 12.
Why can we not replace it with 12?
Because 12's
Because
bigger.
12 is bigger.
And I forgot to put my 6 over here. And then now we swap the 6 and the 3. And now we check again, is 6 less than 8?
Yes.
And 6 less than, oh, you don't have a child, so we're fine. Okay, great. So what's the big O of doing it this way? Log of n, why?
Because you're only doing half.
Half. Basically, it's what you just did, but in reverse. So, that means removing is log of n as well. Or blah, blah, blah. Thus, it requires log of n to both add and remove. Is that better than our other implementations?
Yeah.
Yes.
Sure.
Thank you, Jonah.
Sorry. I'm sorry.
This is actually a really, really short presentation today.
What?
Yeah, we're almost done.
Oh,
yay.
Yay.
Really?
This is really, like, this is really to, wow, I'm just going to stutter 5 more times today. The point of this is that if you select your data structure correctly, you can solve a problem very easily. Towards the end of the class, that's all I'm trying to do, is now that we've gone basic data structures, choosing your data structure wisely makes your problem easy to solve.
So have we covered all the data structures?
No, oh my, no.
Have we covered all the ones we're going to cover this
No, we
week?
still need to do graphs
Graphs.
and B trees.
Graphs seem like they're fun
You know,
to do.
What are
need to, per se.
If I want to believe that you actually have learned your data structures, your basic data structures, then the answer is yes. B trees and graphs.
Okay, let's have this.
What are B
Are there any
trees?
like?
They're like a binary tree, but instead of having only 2 children, you have
3.
As many as you want.
as many as you want.
Oh, no.
No.
Yes! Stop it. Come on, Jonah, embrace
Stop
it.
it.
All right, but we're all right, guys. Back to this presentation. We're focusing on. It is awesome.
Binary trees are fun.
Now, you can use your when you solve this lab, because guess what we're doing in the lab?
Heaps.
No, but close.
Whoa.
What?
What's
Priority
this?
queue.
Priority queues, right?
Hey, I was right. Yes!
She beat me to it.
So,
I was guessing.
if you choose a heap to implement your priority queue, you're probably going to pass this lab pretty quickly. Luckily, the STL actually has a heap implementation, and as surprising it is to me every time, it's not that bad. Usually when I use the STL, sadness occurs, but this time it's actually not that bad. So a heap is a vector that's been heapified. Yeah, I've seen that term used more than once, so I'm going to continue using it because I like it.
It's like
A
a
heap
is-
An apple is a fruit that's been applified.
It's been amplified. Exactly. Exactly.
What?
So, so you create a vector and then you heapify it.
Okay.
Okay? Literally, you use the function called makeHeap to heapify a vector. So you have a vector and then you call makeHeap and then it turns into a heap.
Me make heap.
Did you say
Heapify.
me make heap?
Better than Spotify.
Further, pushes and pops should be done via heap functions, the help functions, heap functions. Push back plus push heap pushes it to the heap, and then pop heap actually pops the heap.
Pop it, drop it, poke it, not it.
That's not it.
Not it. So I think some example code will help here.
That's not it.
I don't know why that top one is hidden at first. So if you create a vector of ints, yes?
I thought these were Java sluts.
Forget, yeah, whatever. I probably should convert these back to real slides, like my own, but
Laziness.
All right, so you create a vector, and then you make a heap that turns the vector into a heap. You okay?
I like pulled my hand up like, yeah, it's kind of like this arm back, and as I came up, I nicked the edge of the table with my fist.
I like our conversations. paradise.
And I just got a crock. No.
So we make a heap. Notice you pass the beginning and the end of your vector. And then you can display the maximum element by just doing v1.front. If you want to enter another element like 50, you do a vector pushback, and then you must call push heap. Now this is the only tricky part. You have to call both functions when you want to actually add something to the heap.
Push back and then push heap.
Right. So you push back, that actually adds 50 to the end of the vector. And then you push heap, telling it that the last element was just pushed. Make sure you percolate up that element as high as it needs to go. Because it's really just a vector.
So push back just puts it on the back. Push heap is the one that actually iterates through and goes.
Right. Pictorially.
Precisely.
Precisely, Robin. All right.
That was quite right in there, Watson.
So push back.
Guys, I'm obviously Sherlock.
Like push back just puts the 5 right there, and then basically increments the size over there. By 1, sorry. So that's what push back does. That's not a heap yet, because you put a 5 right here, and that's not, you've destroyed the heap property, right? So push heap takes this last guy and percolates up. So he goes, okay, we need to swap the 5 and the 6, blah, blah, blah.
Oh, so it does that for you.
Yeah, the push heap is what does this part. That's why I'm saying.
Wow. That's actually kind of nice.
Isn't it? It is. No, it is. It is.
I was being sarcastic
It's-
and serious at the same time.
Right. And then if it needed to percolate up more, it would, or sift up, but it doesn't,
Does
so
it
it
go to the
stops.
actual parent itself?
Yeah, it actually, the push heap will take the last element and percolate it up, is what it does, essentially, on your vector. So that's why you need 2 functions there.
Wait, how do you include the STL
How do you include the STL?
in your code?
Oh, okay, we'll do a code example in a moment. Let me go through
That's
this.
important.
Yeah, I'm sure. And then,
Just don't give us faulty code.
well, we'll go and debug it ourselves, because I haven't done this in a long time. So the maximum element, you can do v up front. If you want to pop it, you do pop heap, and that just gets rid of the maximum element. Notice it doesn't return it, it just removes it. And then does the whole flip and switch, I'm sorry,
Wait.
Switch and flip.
switch and flip. So if we're back to this picture, and you do pop heap, what pop heap does is it removes the 3, takes the 6,
That's not the highest. The last added.
well, we're kind of reversed right here, which is fine.
Oh, so it's wrong.
Not quite. Puts a 6 right here, and then it's going to sift down of the 6. So I'll take, oh wait, we need to swap the 6 and the 5. 5 up here, and then we're done. So pop heap does that whole operation for you. Notice it's not returning the 3 that we removed, it's just deleting the top element. If you need to get the top one, you call dot front.
So you call dot front, and then
Dot front to get it, and then you can pop it afterwards.
and if you put that in a loop, then you would get everything.
Right. And you can do v1.front. Great. Any questions on this before we code it?
No. I actually like what the STL heap. It's not really sadness.
Yeah, this is actually,
Really good.
this is like one of the better things of the STL.
Wait.
Why not just use boost?
What? Why not use boost for a heap? Why? Why would you?
Which one is more efficient?
Which is more efficient?
Question.
Yes.
Does boost even have a heap implementation? Go ahead.
So
I don't know why they
dot
would. They're
front
usually just
gets
appending
the
to.
maximum one.
Yes, unless you reverse the heap.
Okay.
You're allowed to call reverse heap, and that'll reverse
So
it.
what gets the top? Which is our lowest?
Front. So the front's going to get the next element that satisfies the heap property out of all the elements.
Okay. So
Depending
the
on
top
your-
of our tree.
Yeah, the top of your tree.
Okay. That answered my question.
Okay, great. All right, let's go and pause here and do some coding.